So we all know substitution in calculus, where we use u as some function so that it reduces to a simpler integral, and then we integrate it and we substitute the u back in the integral to get the final answer. So solutions by substitution for differential equations sort of take the same approach, and there are three different cases that we can observe. And what would happen is, when we convert a differential equation that is not exact or that looks weird to an equation after substitution, it would reduce to either a linear equation or an exact equation, and we can, or a separable equation, and then we can integrate it easily, find the solution easily, and put the substitution back in. So that is the purpose of substitution. And that is the method of substitution in differential equations. So the first approach involves something called homogeneous equations. First, let's start with a homogeneous function. A function f of x comma y is said to be homogeneous if f of cx comma cy is equal to c raised some number alpha times f of x comma y. If that condition is satisfied, then we call it a homogeneous function. For example, let's just consider the function f of xy equals x squared plus y squared. So this would mean f of cx comma cy is equal to cx squared plus cy squared. That would give us c squared x squared plus c squared y squared, and we could pull c squared out, and we'd end up having x squared plus y squared, which is c squared f of x comma y. Now that is homogeneous. So this is a homogeneous function. On the other hand, let's consider this example. Equals x squared plus y, and I would want to do f of cx comma cy. Then we will have cx squared plus cy, which would give me c squared x squared plus cy. And that cannot be written as c raised some number times f of xy for any alpha. So in that case, this function becomes non-homogeneous. So when we have differential equations, we could make a substitution in terms of homogeneous equations. So if we have a differential equation, first order, m x comma y of dx plus n x comma y of dy equals 0. And if m x comma y and n x comma y are homogeneous functions, of degree alpha, then we can make a substitution u equals y over x, so that the equation now becomes x raised alpha m 1 comma y over x dx plus n one comma y over x dy equals 0. I forgot to multiply by x raised alpha here. Which, if I divide x raised by x raised alpha on both sides, it would reduce to m 1 plus y over, 1 comma y over x is our substitution, which would be u dx plus n 1 comma u dy equals 0. Now, you may say, well, how would I go about solving this? Well, we have a substitution, u is equal to y over x. Since u is y over x, u would also equal to, u times x would be equal to y. Now we could take the derivative and we could write dy over dx using product rule as u times the derivative of x, which is 1, plus x times du over dx. We can go back to that equation and plug in what we derived right here. So divide by dx on both sides, we will have m times 1 comma u plus n times 1 comma u dy over dx equals 0, which would then become m times 1 comma u plus n times 1 comma u plus x times du over dx equals 0. And if we rearrange things here, we will have m times 1 comma u plus u times n of 1 comma u plus x times n 1 comma u du over dx equals 0. If I move terms to the other side, this equation eventually is going to either become a separable equation or it is going to become a linear equation. And I'll show that using an example. So what we had earlier wasn't separable, but if it is homogeneous, then with a proper substitution, we can either convert it to a separable equation or a linear equation and use one of the methods that we've used in the past and carry forward here. Well, is that the only way of doing it? Well, I could make a different substitution and I'll get the same answer. So instead of saying u equals y over x, I could also say v equals x over y, in which case the differential equation would become x over y comma 1 plus n times x over y comma 1 hit times dx x comma y comma 1 dy equals 0. I could rewrite it in terms of the substitution. M v comma 1 dx plus n v comma 1 dy equals 0. At this point, we know v is equal to x over y, which should imply v times y would equal x. So we can take the derivative with respect to x, and we will have, using product rule, v times dy over dx plus y times dv over dx equals 1. Let me see, I think I'm making a slight mistake here. The better way of doing this. So we would have v equals x over y, which would mean x would equal v times y, and we have to take the derivative with respect to y in this case. So dx would equal to v times dy plus y times dv. So we can make use of that substitution and get to the answer. So it doesn't matter which way we do it. You can either use the u substitution like we did here, or we could do the v substitution like we did there. So it's entirely up to you. And once we are done with that, we could go back here and substitute in the equation for dy and come to a similar expression like that, and that would be either separable or it would be linear, and we can use one of the previous approaches to get to the answer. So if we look at this equation, I have m v comma 1 dx plus n v comma 1 dy equals 0, and I could plug what I have derived here in the equation. So I can either plug it for dx, plug it in for dx, or I can plug it in for dy, or I could plug it in for dx dy over dx. It's entirely up to you. It's a matter of convenience. So if I simply plug it in for dy over dx, I could rewrite this as and we have dx equals v times dy plus y times dv. Divide by dx on both sides, so you have 1 v times dy over dx plus y dv over dx equals, and we take that and solve for dy over dx. We have 1 minus y times dv over dx equals v times dy over dx. Then we can take this expression, plug it back in that expression, and arrive at something like this, and we can proceed to solve. So once we solve it, we can go back and take the substitution that we initially used and replace it in the solution. So that is the first way, and that substitution will only work if we have homogeneous equations. And we require both m as well as n to be homogeneous. Another approach is the Bernoulli equation. It is a very special kind of equation. Just like a first order linear equation that follows a specific pattern, this Bernoulli equation will also have a very specific pattern. An equation of the form dy over dx plus some function of x, p of x, times y equal to some function of x, f of x, times y raised n is a Bernoulli equation. It has to follow that pattern. If it did, then by default the substitution is u equals y raised 1 minus n. And here n has to be greater than or equal to 2. In the other cases, it will simply reduce to a linear equation or a separable equation. So a Bernoulli equation has a very specific format, and that is the format, and n has to be greater than or equal to 2. And if that is the case, then we always make the substitution u equals y raised 1 minus n. And when we make that substitution, the original Bernoulli equation would either change into a linear equation, or it is going to change into a separable equation. So the objective is to take a Bernoulli equation and change it to a linear equation or a separable equation, and use one of the techniques that we use for linear and separable equations to find the answer. And the last type of substitution that we are interested in a differential equation is a functional expression. So this is called reducing to separation of variables. Or a separable equation. So we take a differential equation that is not separable. We are going to make a substitution, and once we make a substitution, we are going to convert it to a separable equation. And we all know if we convert a problem to a separable equation, things become easy. So that is the goal of this substitution. So what is the original DE? The original DE is one that is going to look like dy over dx equals some function g of ax plus by plus c. Here b cannot equal 0. If that is the case, the substitution u equals ax plus by plus c, which would be the part right here in the function, will reduce the original dE to a separable dE. And we could use the method that we used for separability and find the solution. An important remark here is, regardless of what type we have, do not forget to substitute the variable used for substitution in the solution using the original variables in the dE. What do I mean by that? So let's go back to the very first case where we converted a homogeneous equation. We used the substitution u equals y over x. We changed the equation to a different form, and that form is right over here, and we are going to use that to perform or obtain our solution, and that solution would be in terms of u and x. So we have to go back and resubstitute u to get the correct answer in terms of y and x. Same with Bernoulli. If you identify an equation to be Bernoulli, we use the substitution u equals y raised 1 minus n, and once we do that, we will reduce it to a linear equation or a separable equation, and once we get the solution, we have to substitute u with whatever substitution that we used initially. And same with the last case, where we reduce it to a separable equation. If we use a equals ax plus by plus c, we have to go back and replace the u in the solution with ax plus by plus c.